Hello everyone, in this video I'm going to talk about errors in Python. I've touched on this a few times in previous videos, but now we're going to go more in depth on the topic. There are two types of errors in Python, syntax and runtime. Syntax errors are the easiest to detect because they are caused by mistakes that will prevent the code from even compiling in the first place. Just a quick refresher, whenever we execute Python code, it has to be compiled into bytecode before execution. But in order to do that, Python needs to check all of our code to ensure we have obeyed all syntactical rules. These rules include indentation levels, how we assign variables, how we define functions and classes, using special characters properly, stuff like that. If anything is out of place, Python will stop and report the syntax error. And I've got an example right here, and as you can see, as with a lot of code editors that have really good capabilities like VS Code, it's really hard to miss a syntax error because it'll get highlighted almost immediately. And VS Code utilizes the Python extension that includes the program called Pylance, which is what does all the checking beforehand and highlight any problems so you can fix it before you waste time trying to execute it. See, this is a message from Pylance saying, hey, you got to have something on the other side of that equal sign. Other code editors that support Python also have this sort of thing where they utilize some outside program to check your code as you type it. So if I run this program, Python will say, hey, we can't compile this because some of your code is wrong. We don't recognize this as valid syntax. And it's basically indicating you need to have something on the other side of that equal sign. So that's a basic syntax error. Runtime errors, on the other hand, cannot be detected during compilation and can be harder to detect in general. There are two types of runtime errors, logical and exceptions. Logical errors are more difficult to deal with because the problems they can cause are not always immediately detectable. The code is syntactically correct, but there could be issues like incorrect data being provided, code was executed out of order, or maybe some lines were left out entirely. There are a number of causes for logical errors, and we usually won't notice it until after the program has finished running because it is typically the results that are impacted. I have an example of a logical error right here. We're going to pretend that this data is actually in a file. I wanted to keep things organized and all in one place, so it's actually in a list, but we're going to pretend it's in a file and it's still formatted the same way. We've got two lines of data and they're separated by spaces, in some cases, multiple spaces. Now, at the very basic level of reading in data to be processed, you wouldn't have that data separated by spaces. You would, at the very least, make them comma separated values. But we're going to say that a total amateur wrote this and didn't know better, and they decided to separate everything by spaces. And then down here, we're going to process this data that we're reading from a quote unquote file. Line by line, we start by splitting up each line by the space delimiter, which creates a list and it stores it in this variable called line. And then we access the first four elements, which should be the only four elements in the line, and we put them in a tuple, which is then stored in the pinfo list. And then down here, we just read out the data and print it out. So when I run this, as you can see, Crozo started off good at first because it printed out the name, it printed out their ID because there was only one space between them. But then we get an empty space right here. And that's because there are two empty spaces between the ID number and frigate. So when it's split between the two, we got an extra piece of information stored in the line variable, which unfortunately caused frigate to be printed in on the final part, which should have been the frigate's name rather than the ship type. So Hawk got lost completely. And then with Ben, Ben was even worse off because there's multiple spaces between Ben's name and his ID. So his whole info line was basically just his name followed by a bunch of blank spaces. So the most obvious thing here that people would see as the logical error, and probably the easiest to fix, is the fact that it was space delimited. Now, in general, it's not necessarily bad to space delimit, but it's probably the least recommended way to delimit data, especially if there might be data pieces that contain spaces themselves, and you would end up unintentionally breaking that data apart. But the big issue is that multiple spaces were used in between certain pieces of data, like between Ben and his ID number, Crozo's ID number, and his ship type. That's what causes problem, is because it saw multiple spaces, so it split that up, and as a result, it created an empty string element inside the line. In Ben's case, it created multiple empty string elements inside the line. An easy fix, if you really had to have space delimited data, is to delete all those extra spaces. So if I run it now, the information is now all there, correct? Because we got rid of all those empty spaces, there are no more empty strings being put inside the tuple, because now the line really is only 4 elements long. Another way to fix it is to do away with spaces entirely and replace it with commas. And then we update the split to look for commas instead of spaces. So when we run it again, we get the exact same results. So there's a couple of ways to fix certain logical errors. It will often depend on what the situation is. In some cases, there are multiple fixes. In other cases, there might only be one fix. And so that's an example of logical errors. There are all kinds of logical errors that can happen in our code. They could be math related, they could be file IO related, it could be network related, it could be all kinds of things. So it's really important to make sure that our code is behaving as it should. As I mentioned in the beginning, logical errors are by far one of the most difficult things to catch in a program. So really the only way to really detect that there's a logical error happening is by paying attention to the end results, the data that is most likely to be impacted by this logical error. Exceptions, however, are runtime errors that will cause Python to react. When an exception occurs, it is referred to as raising an exception. When raised, they will by default result in a message printed out explaining the error, followed by forcibly stopping the program. I have an example right here that will trigger an exception. This one will cause the zero division error exception. It's because we're trying to divide by 0, which is mathematically impossible. So when I run this, we get the message. It contains 2 parts. The first part is the traceback here, and the second part is a short explanation of what caused the exception. The traceback shows the code that triggered the exception. At the bottom of the trace, it starts with the line of code that caused the exception. Depending on the exception, this may be the only line in the trace, but the trace can potentially be longer depending on how deep in the code the error occurs. In fact, if I contain this all in functions, so we'll hide this under test, then we'll create a main that will call test, and then we'll call main. And then if I run it again, so as you can see, we've got a longer traceback because there are layers to this. So at the very bottom, we see that we've got the code that actually caused the error, where we divided by 0. At the very top, we've got our main function call. This is where our code pretty much started. In fact, whenever you have a main and we've got functions, all kinds of stuff going on, usually the very first line is going to be saying, hey, when you called main, all of this happened. And so it says, okay, so in this module where you called main, it then says in main where you called test, and then in test, here's the problem that occurred. Sometimes a traceback won't end with our code. It'll actually end at a very much deeper level. Sometimes it will end somewhere inside the Python source code saying, hey, because of what you put in this code, it actually caused a problem within our own code. But even when that happens, it's still our code's fault that this happened in the first place, because it's usually something that we didn't account for. Maybe we forgot to check for something before passing it into a function, and then it caused the error. Like when you open files for reading, it's usually a good idea to check to make sure they exist before you attempt to do so. Otherwise, you're going to get a file not found error. But because of that, because of how big a traceback can get, it can sometimes get very messy and pretty difficult to read. But as long as you can find the last line from our own code that caused the error, then usually you can find the issue and fix it. So because of that, tracebacks can tend to be a bit big and sometimes a little hard to read, but they are incredibly helpful for you identifying the line of code that caused the problem in the first place. The explanation of the exception is divided into 2 parts as well. The exception class that was triggered, which is right here, zero division error, and the message explaining why it was triggered, which is right here. We try to divide by 0. The messages are usually pretty good at explaining the problem, but some exceptions, especially those from third-party modules, might be a bit confusing. Now, the good news about exceptions. We are able to proactively deal with them to ensure that our program can either work around the issue, or at the very least, quit gracefully in order to preserve whatever progress or data that has been made. We can even use this to log the error before moving on. We do this by using try-except statements. We start with a try block, which we establish with a try keyword like we do right here, and then we place the code that will potentially trigger an exception under this block, which we have this line right here, which will definitely cause an exception. And as you can see here, we are not just limited to placing the single line of code that can cause problems in the try block. Where applicable, multiple lines of code that can each cause their own exceptions can be grouped together under the same try block. This means you're not required to start a try block for each problematic line. And non-problematic code, like that print statement right there, especially if they work with the problematic ones. like setting variables or calling other functions. All of this will help keep your code organized and readable while also dealing with the exceptions. Once you have the try block completed, we need to follow it up with the accept block, which we've got right here. This is where we define which exceptions to catch should they be raised. There are a couple of ways to write this block. The first way, as I have right here, is to have a blank accept statement. However, it is highly recommended against doing this because it can catch exceptions that you would want to avoid catching unless you know what you are doing. A good example of this is the keyboard interrupt exception, which occurs when you use something like Control C to forcibly end a program. And if I run this code real quick, can't divide by 0. So that's my little print statement I put here to happen when we catch an exception. The second way is to specify an exception. Exceptions are defined by classes, so we can specify the class name of the exception that may be raised in this statement. We can also just specify the exception class if we wanted to, because the majority of exception classes inherit from it. So specifying the exception class here instead of zero division error could still catch the error. A quick note before I continue. While the exception class is a parent class for all the exceptions we would want to catch, it is also a child class. It inherits from a class called base exception. We could write an accept statement to catch this as well, and it would work in a similar way to catching the exception class. However, this also comes with the same flaw as a blank accept statement. You will risk catching exceptions you shouldn't be catching. So it's just another one of those things that you should only do if you know what you are doing. And real quick, just to demonstrate this file as well. So this time we are specifically catching the zero division error. We'll still get the same message, but this message will only trigger if we specifically catch this. If another exception were to occur inside this try block for some reason and we weren't catching it, the accept would ignore it because it's not the zero division error. So when I run it, we still get the same message because we caught that zero division error. The third way is similar to the second way, but we use the as keyword to specify a variable name for the exception. This is so that we can work with the exception directly. One reason we would do this is to still have the exception message print out to the screen without stopping the program. We can also use this to log the exception occurrence to a file so that it can be reviewed later. Exceptions may also have additional attributes that provide useful debugging information, and we would be able to access them when catching the exceptions this way as well. For example, this is a very basic example, but there could be other attributes as well. But for this one, I'm accessing the magic attribute traceback in order to access the traceback information from the exception, and which I then immediately pass into this function here, which will print out the traceback for me. Because we can't just print out the traceback directly, it will just give us a little address saying, hey, there's a traceback object here. In order for us to actually print out the information, we have to pass it into this function here from this module, which you have to import. But other than that, this example right here is mostly the same. We have the same code, we still have to try accept, we're still catching zero division error, but then we have as E. Now, E is a very common name to use for a variable for any exception you catch. And because they will only exist from within this accept statement, you can use it as many times as you like. So, but in here, it's just very basic. I'm accessing the traceback from the exception object. And I'm going to print a little line here to separate the traceback from the error message. The error message you get from just printing out the exception directly. So if I run this, so it prints out our little traceback here, and then it prints out the error. Now, when you print out the error, it's not going to print out the class name. So if you want it to print out the class name, you will have to code it to include the class name. And I'm just going to show a very simplistic way of doing that, since most of the time when you're printing out the error or something like that, you don't really care about the error class name. You just want a really good description of what went wrong in the program. And then if we run it again, zero division error. So it would look like it would normally would if we just let the exception fall through and it would crash the program. But there are tons of other things that we can do in exception statement. We don't have to just print out the error name and the traceback and stuff like that. We can get it to do anything really. We can have it log the information to a file so that it can be reviewed later. We can have it print out a nicer, more understandable message on the screen for anyone, especially those who might not be super tech savvy that might be using the program. We can even just have it ignore the error entirely and move on if it's not that super critical. There's a lot of things we can do with this, and it really just depends on what you need it to do. So that's how you would handle exceptions in general. And I would say that this third way is the best way to do it. The second way is also pretty good if you just don't care about the exception itself. You just want to stop it from crashing your program. But if you really want to provide really good debugging information, I would say catching it by name is usually the best way to do it. Now, as I mentioned earlier, we could put multiple lines of code that can cause all kinds of exceptions and stuff. under a single try except statement. There's multiple ways of handling it, and they're all pretty simple and they're all pretty straightforward. And it keeps your code clean and readable so you don't have a bunch of try except statements cluttering your file. And I've got this example right here. I got 3 functions. They're all going to just raise an error. So we have a file exists error in function 1. Function 2 is zero division error, and function 3 is the file not found error. And I'm going to run this a couple of times, and each time I'm going to comment these out one by one so you can see that this will catch all of them. Now, for this first run through, we're just catching exception. I want to show that exception can catch all of these. Actually, you know what? Let's change that to as E and just have this print out E. Actually, let's have it print out type instead, because I don't think I called these right, so they may not print out messages. So let's just print out the type, so that will guarantee show how this works. So we're going to run it the first time. It's going to trigger the file exists error. See, so it catches that. Comment that out. Run it again. We now get the zero division error. Run it again. Now we get the file not found error. So that's one way to do it. It's just to catch the exception class itself, because any exception classes that inherit from this class that can potentially be raised will be caught by this except statement. However, when you're expecting multiple different exceptions to be triggered potentially, it's still recommended to try to catch them specifically, particularly because sometimes you might have different exceptions that need to be handled differently when they're raised. And there are multiple ways that we can do this. So the first way we can do it is to have multiple except blocks for a single try block, like so. Now in this example, this is probably not the best way to do it since they're all doing the exact same thing. However, if you have multiple radically different exceptions that could potentially occur in a single try block, then you would probably want to catch them all separately so that you can handle them all in a different fashion. So if I run it, there's our file exists error, our zero division error, and our file not found error. And if all the exceptions that could potentially occur in your program didn't have to be handled differently, like they could all be handled the same way, then we can have them all in a single except statement. And inside the single except statement, we would create a tuple containing all the exception classes that we would expect to catch. And so in the case of this example, if it comes across any of these 3 exceptions, it's going to assign it to E and then execute the code under the except block. So this is a perfectly valid way to do this as well. And if I run it, file exists error, zero division error, and file not found error. So that's how you can handle multiple exceptions at once. One last thing to talk about. We can build our own exceptions. This is particularly useful for when we are building our own modules for other programmers to use. Raising your own unique custom exception can help them identify issues that could otherwise be hard to debug. And it's pretty simple. All it requires is a little bit of inheritance. So I've got an exception called the bad ship type error, and it inherits from the exception class. Really, the only thing you really have to override is the magic method in it. And you can define it however you want. You can have some arguments, you can have no arguments. Although if you're not going to have arguments, then there's probably no point in overriding in it in the first place, but it's however you want to do it. If you need to, you could technically just have the whole thing blank. You can just define this class here and type pass, and that'd be good enough. So I have 2 arguments for this one. I have the argument ship type, and then I have the argument message, and message has a default value that says invalid ship type. We can also create our own attributes for our custom exception class if we need to. This is useful for storing extra information to help with debugging. In this example, I have 2. I have ship type, so my custom class will store the ship type information, and then it stores an attribute for the message. Now, the message one actually might be a little bit unnecessary considering that we're calling super to access our parent class stuff, and that's going to be storing a message for us anyways. So, in order to trigger this exception, I made a function called register ship. It's going to take in 2 arguments, ship type and ship name. It's going to check to see if the ship type is in this list right here. And so the only ship types that are allowed are frigate, cruiser, and cargo. As long as it's one of those, it will print out this message here where it says ship type registered and the name of the ship. If the ship type is not in that list, then it will raise the bad ship type error. And then we call the function twice down here, where the first time we pass in frigate and hawk, so that will work just fine. But the second time we pass in a ship type called blob. So obviously that's not going to work because it's not in this list. So when I run this, so we see forget registered hawk, that worked just fine. And then down here, we've got our traceback, we've got main, and inside main, we see the function call register ship, where the parameters blob and morpho were passed in. And that triggered the raise bad ship type error. Here's the error, and here's the message, invalid ship type, blob. And so that's how you can create your own custom exceptions. And this is pretty useful, whether you're building a module for other people to use in their Python programs, or you're building a Python program yourself. Being able to create your own custom exceptions will make tracking down errors and debugging them much easier, not just for you, but for the end user that you're making this program for. And that's it for errors in Python. So I hope you've enjoyed this video and found it helpful, and if you did, then please hit the like button and leave a comment below to let me know what you think. And if you want to see more, head on over to Wayfair Coding Academy channel to check out my other content. And while you're there, subscribe to the channel to stay up to date on new stuff as it comes out. Thanks for watching, and I'll see you all next time.